Now that we have introduced linear models and have covered some common practices and metrics for evaluation, this video will provide a conceptual overview of several common models used in practice. Although later modules will introduce additional modeling approaches, this is meant to provide you with the foundational knowledge needed to start experimenting with these models with real data. To recap from an earlier video, we have already introduced linear regression and logistic regression and emphasized that they are able to find linear relationships in data. But let's now look at decision trees as a modeling approach. Decision trees are a type of nonlinear or nonparametric model. Unlike the assumptions that are required by linear models, decision trees are not so sensitive to multicollinearity and are able to model more complex relationships within data. A decision tree will identify the most predictive features and will split them to form a tree-like structure. The model breaks data down into smaller and smaller subgroups with each split. For example, let's look at a more realistic representation of study time compared to test scores, where we can see that the relationship is neither linear nor consistent across the x-axis. Even just using this one predictor of study time to predict test score, the decision tree will identify split points within our data. So again, we give it study time and it's identifying where to split that feature. And it's able to then learn different relationships within the identified subgroups. The resulting tree in this case might look something like this, where it's split on study time again twice, but it's able to kind of break up the data into smaller subgroups and then find the relationships that are better represented within those subgroups. There are different variants of decision trees for different modeling tasks as well. Regression trees can be used to model continuous data, like we see here, or classification trees might be used for categorical or binary data. There are different methods that can be used to determine how the tree is formed and how features are selected and split. While not quite as interpretable as linear regression, decision trees do place more important predictors near the top or the root of the tree. There are a few modeling decisions, or hyperparameters as they're commonly referred to, that need to be set when training decision trees. Among these, the application of pruning is a common practice which can help reduce the complexity of the model. This is particularly helpful as these models can be prone to overfitting, where the model is more complex than is needed to represent the relationships in our data. Beyond this, other common parameters include the minimum leaf size, which limits the size of our subgroups, the maximum height of the tree, so basically how many splits do we want to make across our variables, and the split method, which determines again how it identifies the important features and how they are split. Another common modeling approach, naive Bayes, takes a more probabilistic approach to modeling data. This model is based on Bayes' theorem. This theorem states that the probability of some event A happening given B happening is equal to the probability of B given A times the probability of A occurring divided by the probability of B occurring. So let's break this down and give it an actual concrete example. So if A is the student getting a high score on a test and B is the student having studied, we can calculate the probability of the student getting a high score having studied based on the occurrence rates of each of these events. So in short, it describes the probability of something happening while accounting for the likelihood of those events occurring independently of each other. This starts to describe a probabilistic relationship between variables within our data. So typically used for classification, naive Bayes is rather easy to train because we're just calculating the occurrences of these events within our data. And this is the case even with large data sets. This type of model works particularly well when you have a large number of features. However, like linear regression, this model does assume that the features are independent. So if you have features that are highly correlated with each other, that could cause issues for this model. And the last type of model that we'll introduce here is the SVM, or Support Vector Machine Model. In terms of similarity, SVMs can function similarly to logistic regression, where its goal is to separate positive and negative labels, but works well when there is a large number of ambiguous or misclassified cases, or potentially misclassified cases. So to help visualize this, let's use an example where we want to predict whether students get high or low scores on their test, indicated by the red and blue dots here. And we want to use two predictors of study time and the amount of sleep that students had. In this hypothetical example, let's say that we have a nice separation of these labels, just like we see here. The line that best separates these groups might pass right through the middle here, especially if we're calculating for logistic regression, for example. But there are many possible lines that work in this scenario. There are a lot of lines that effectively separate out these two classes. Now let's say that we collect more data and we end up with this additional low score that is notably close to the group of high scores that we had from before. If we refit the line now, we can still separate the values, but this leaves very little room for error. So in this case, a model might learn that this is the best fit line, again, because it's still able to separate out all of the data, even though it's maybe questionable whether or not this would generalize well in practice. We may now end up with a large number of high scores misclassified since they're so close to that prediction boundary. Even in this case, it might still be ideal to keep the boundary line between the two groups kind of where we had it before, even if that leads to a misclassification of that new sample that we had collected. SVMs work by identifying the boundary of groups, of these kind of groups of labels, and using those boundaries to draw support vectors. So basically, a support vector is the boundary of one of those groups. It's usually a point or represented as kind of a line that forms the boundary of a cluster of similarly labeled samples. So rather than fitting a line, we are effectively fitting a buffer or a margin between these groups, which allows for some degree of ambiguity to exist within. The model incorporates this misclassification trade-off into its training, typically resulting in a classification boundary that is more generalizable in practice. While the base case for SVMs use a linear function determined by a hyperparameter called the kernel, so if we use a linear kernel, we are effectively fitting a line to separate our data. We could use additional kernels to emulate other functions. So we could use nonlinear kernels to fit nonlinear functions to our data as well.